right, guys, let's go ahead and get started. Today's date at the top of your notes. We're not starting chapter 2. We're going to finish chapter 1. But we're going to be talking for several days about systems of equations. If I don't see another word, just leave it at systems of equations. Do you know what I'm talking about? What is that referring to? Systems of equations. Anybody? Any thoughts on that? No, really? Because you did this in Algebra 1 and a little bit in pre-Algebra 2. It's not clicking with you? Nothing's coming to mind? It's where you have a pair of equations or more, but you have more than one equation that describes the same x and y. It happens in linear equations where we have more than one descriptor describing the same x and y. Let's just pretend for a minute that we were going to do a little fundraiser in the start first period, and we're going to make some calendars. Okay? We could use artwork, we could use photographs, we could use whatever you want to make these calendars. And we're going to print them and sell them for $15 each. All right, that's going to be our fundraiser. We're gonna print them. We're gonna sell them for $15 each. So we sell 100. We bring in $1,500, right? We sell 200. We bring in $3,000. You with me? Do we get to keep every cent of that? Is every cent of that $1,500 or $3,000 going to be sheer profit that we get to use on our blowout first period class vacation that we're going to take? No, why not? We're talking real world here. Why don't we get the whole $3,000 to use on our little class vacation?
Because most of that had to go into calendars.
Okay, you have a product that you have to create, don't you? So let's think about what goes into the creating of the project. We know we're getting $15 for every calendar, so that's how much income we're going to be bringing in. So if I were writing an equation for that, for like how much money is going to be coming in, and I have two variables, the number of calendars that are sold and the number of income we make, right? How could you write an equation for how much income is going to come in on $15 a calendar? If X is going to stand for like our number of calendars, in fact, let's go ahead and write that down. Let's say our calendars are $15, and if we're putting a title on this, we're solving systems of equations. So writing down a few facts about this here. We've got our calendars are going to cost $15. And we're going to let X stand for the number of calendars that are sold. That'll be our independent variable, and how many calendars we sell is going to affect what? How much money we make, our income. That'll be our second, the dollars that we earn. All right, you with me so far? So let's write that first little equation, that little equation for our income equation here. What is that going to be? Think about it for a second. $15 for every calendar. X is the number of calendars. Y is the income. Help me write a simple little equation for that. First period.
15x.
Thank you so much, Abby. 15x equals y, or the income is going to equal 15 times x. Beautiful. That's awesome. Now, as Lane just mentioned, we're not going to get all of that income to get to spend on our little class trip. We're going to have some expenses, aren't we? There's going to be some expenses affiliated with making this product. What can you think of that would be affiliated? What kind of expenses are we going to incur in making a calendar? Let's think about it for a second. Brainstorm with me. Printing. Okay, so printing will be like I've got to pay for the paper and the ink that goes into the calendar, right? That shiny, glossy calendar paper. That's going to be an expense for sure. Can you think of other expenses that may come along with it?
So the art maybe that you're going to
Yeah, some of the art. Now, even if we use each of your individual art projects from art class, there's still going to be like a design. Someone's going to have to put it all together and design it and put it into our format that we need, right? And put the calendar and the dates and arrange it. We're going to need somebody to do some of the artwork involved. Everybody agree with that? All right, so let's say if we're going to need like a design person, we're going to have to have some dollars to go in the design. whether we're paying for the artwork or just arranging it. And then we're, of course, going to have some printing fees. Help me think of what are some reasonable amounts here. Let's see. Design. What do we want to say? Maybe we could get somebody to do it for like an even $100, you think? $100 to arrange our calendars? Yeah, let's say we could do that. Let's say we could pay somebody $100 to arrange our calendar. What do you suppose it's going to cost to print on that shiny glossy paper, a calendar, to print it with, color ink and all of that? What do you think it's going to cost per calendar? Let's just make a number. What do you think? You think $5? That's pretty high, but maybe. $5, $3? What do you want it to be? We're picking. You're going with 3. Okay, Parker says it's going to be $3 for printing. He's found us a deal. Awesome. $3 a calendar for printing, right? So I'm going to write an equation with the same X, number of calendars, and the same Y, how much it's going to be costing there. And what is that? What would that equation look like? What do I do with the 100? I'm subtracting it from the money, yes, or in other words, but I've also got the printing. What am I going to do with this $3 per calendar? I've got to add it to X, $3 plus X, $3 times X. So I'm going to have 3 times X. Actually, the cost of printing is going to be added to the cost of the design. Those two go together, don't they? The printing cost and the design cost go together and come out to our expenses, our dollars again. Okay, so 15 times the number of calendars gives us the dollars. 3 times the number of calendars plus 100 also gives us the dollars, right? So we're trying to find an X and a Y that works for both of these. Making sense? You with me? That is an example of a system of equations. Now, that's all I wanted you to think about is how you can have 2 different equations describing the same X and Y. Let's talk about methods for solving that. That's what's pretty much going to be on this next test is we're going to talk through methods for solving these systems. The first method we're going to do is solve by graphing. I like to do this one first because it gives you a visual picture of what we're looking for when we solve a system of equations. So for example 1, we're going to have the 2 equations, x plus y equals 3, and negative 2x plus y equals negative 6. Both pretty simple, straightforward equations. Excuse me. Now, if you would, take out a sheet of graph paper, regular graph paper. We talked about that from the beginning that we need to have some. Sometimes Ms. Olson graph paper works, but other times we'll need an actual sheet of it when our numbers are going to get a little larger than what would fit on the small graph. If I'm going to graph these 2 equations, what do I have to do first? Slope-intercept form. I need to take each of them and get them in slope-intercept form. I'm going to draw an arrow. If you need a little more space to rearrange, do so, but write the rearranged equations over here on the right. Rearrange each of them to isolate y so that we can graph. First one's pretty simple. Make sure your signs are all correct. Second one's also pretty simple. Both of those rearranged in one little easy step, didn't they? All your signs correct? All right, so looking at this, before I go to my graph, I can know a little bit about about the size of the graph I'm about to do. I can tell that this one's going to start at positive 3 and this one's going to start at negative 6. So I know I'm looking at a pretty large graph here, right? It needs to have a pretty significant y-axis. This one's going to have a negative slope. Show me what a negative slope is going to look like. Going down this way. This one's going to have a positive slope that's 2 over 1. Can you visualize what that's going to look like? Is that going to be pretty much like an even 45-degree angle? Is it going to be steeper? Is it going to be shallower? What is our slope of 2 over 1 going to look like? It's pretty steep. Yes, when you have a whole number slope higher than 1, it's going to get steep. The higher the number, the steeper the slope is. So on my graph paper, I'm not going to use the whole sheet, but I am going to make myself a pretty significant y-axis. So over here on the right-hand side, put today's date. So it'll match your notes. You can tell where these examples are. And then over here, I'm going to write example 1 so I can match them. Give myself a little bit of room for negative x's. So maybe I'll start my y-axis right about here. And kind of count down. Make sure you're leaving yourself plenty of room. That's probably about long enough. Make sure I'm giving myself lots of room there. Go ahead and make your x-axis. Put your arrows on the end. All right, let's graph that first equation together. That first equation was y equals negative x plus 3. Graph that one carefully. Negative x plus 3. Negative x. What is the slope on negative x, Max?
Down 3/1.
No, that's the y-intercept. Remember, slope is always in front of x.
Oh,
so what is the slope here? It's okay.
I was thinking that, sorry,
It's okay.
just down 1
It's negative 1, which means down 1
over
1 over positive 1. Negative 1, positive 1, negative 1, positive 1. Go ahead and make yourself plenty of dots. You can make a straight line really easily if you've got points all the way to the edge. Up 1 over 1. Do I have to worry about dotted lines, dashed line, straight line here? No, when do we worry about dashed line, straight line? In inequalities. These are equations. We don't have to worry about that. Just connect it. Connect carefully. I can't emphasize enough that the points are really important. When it comes to solving systems, it matters if your line drifts away from where it's supposed to be. It really, really matters. So put the points all the way to the edge. Be detailed. Do not sketch on a system of equations. You can't solve by a rough sketch. All right, let's grab the second one. Go ahead and graph it yourself. Started at negative 6. Up 2 over 1. Points all the way, don't sketch. Up 2 over 1 all the way. Once you have points all the way from top to bottom, connect them. Connect carefully. Don't let your line drift off the points. Good points. Those look fantastic. Very nice. Good job. Let's go ahead and move. What's your points? Good. Very nice. Very nice. All right, fantastic. Very precise work, first period. Good job. All right, where am I going to find a solution where x and y is true for both of them? Remembering that that whole line, everything on that line is an xy that's true for this equation. And every single place on this line is an xy that's true for this equation. Do I just mean the points? No, I mean, you see that ugly point right there? That one right there? See that? That is an xy solution that's true for this equation. I don't know what it is. It's something like x is 8.3, y is 6.1, something like that. But every point on that line is a solution that is true for that equation. Where do I find solutions that are true for both? It's where they cross. That right there, Max, is the one place where I have a solution that is true for this equation and for this equation, right? Is it possible to take two straight lines and have them cross at more than one place? If they're both straight? No, they're going to cross at one place, right? Unless there's only one possible time they could ever cross at more than one place. If they are parallel. If it's one directly on top of another. And if you think, well, why would it ever look, why would that, I mean, that's the same equation. Why would you ever have one directly on top of each other? sometimes you can have the same equation written two different ways. You know how we rearrange it, and you may not realize it's the same equation. So it's possible to have the same equation written two different ways, and then you realize, oh, all the solutions are the same on that one. But most of the time, there's going to be one. Can you name that point for me? That one solution that is true for both of these? 3, 0. So come back over here to your notes, and I want you to write the solution is the point 3, 0. What that means is that is a point that works for both of them. Take just a second. Let's just waste just a second plugging it in and testing that. I want you to really understand what this does. If I put in a 3 for x right here, I get -3 plus 3, which equals 0. And if I put in a 3 right here, I get 2 times 3, which is 6, minus 6, which is 0. That point works for both of them, not if you're getting it. Okay, awesome. Go back to your regular paper. Let's do example 2. I want you to try this one without me. Take the equation -8x plus 2y equals 20. And the second equation, -4x plus y equals 3. Rearrange those and graph them, please. You've got plenty of room on that sheet of graph paper. Just maybe come down here to this big wide open area and make yourself a second one. Check and see if you rearranged correctly. Did you know what was going to happen as soon as you saw this graph? When you were looking at the two equations, did you know what was going to happen? What ended up happening? They're parallel to each other. How could we have known that they were going to be parallel? What did we learn about parallel and perpendicular already? When we see that they end up having the same slope, we should know that they're going to be parallel. But graphing it gives us a really good picture about what that means. How is it significant? Why is it important that they are parallel? What does that mean in terms of finding a solution for the two of them? Wait for one of you. What does that mean in terms of finding a solution? There is none. There's not going to be a single place where these two lines ever touch, is there? There's not going to be any common solution that they have. No place that is true for both of them. So what do we write on that? We write no solution. That's right. It's a null set or a no solution. Awesome. Any questions so far? Is this coming back to you? Do you remember this from Algebra 1? Pretty easy stuff. All right. Let's graph one where we're going to need to use our computer. Let's just look at this for just a second. And we're going to call this one Example 3. Write with me for a second. And then I'm going to pull this word problem up here for you to look at. This is from my old book. And I'm going to zoom it in so you can read it with me. But I really liked this example. I want us to look at it together. All right, so Southeast Publishing, this is kind of similar to our little calendar example we just talked about. Southeast Publishing paid $96,000 to an author for the rights to publish her book. That sounds amazing, doesn't it? $96,000 to an author for the rights to publish her book. If one book costs $12 to produce and they plan to sell them for $24 each, how many books must Southeast Publishing sell to break even? Show your results, and then we're going to solve this by graphing. So let's think about a break-even point. This is a really good practical application for when you would use a system of equations. A break-even point is something every business has to find, right? You have to find, if you are producing some good or some product, you have to find the point at which the income that you make from selling it exceeds the outgo that you spend on producing it, right? Anything you can think of at all, from making yogurt to making shoes to anything at all. Your income has to exceed your outgo, what you're spending, or you're not making a profit in your business. Yes? All right, so let's talk about writing an equation for each of these. For the first one, the income equation for this Southeast Publishing is going to be really simple. How do you calculate the income? Is that affected by the income? Is that affected by the $96,000, by the $12, or by the $24, or by several of them? Which one of those numbers affects the income, the amount of money that they're going to be bringing in? How much they sell them for. The $96,000 is an expenditure, isn't it? That's what they're going to spend. Follow? The $12, that's another lane expenditure. That's what they're going to spend, but the $24 is an income. So write that down on your paper with me. Our income here is going to be $24 for every book that they sell, right? What are our variables going to be in this particular equation? What is the product that they're selling that we're hoping we'll sell more of or less than? What? Books. So X can be our number of books. And what is the number of books going to affect or impact?
The amount of money.
The amount of money. That's right. Y is going to stand for the dollars that are coming in. So as far as the income, that Y, is going to be what number? What did Laurel just say? Jason, the $24 times the number of books. That's the whole income right there, isn't it? $24 for every book. Not if you're with me. Now let's figure out their expenditures. How much they're going to be spending. All right? That total dollar amount is going to be affected by what two things in this problem? Or what things in this problem? The $96,000, that's definitely an expenditure, isn't it? A big expenditure. And the $12 per book, 12 for every book. So $96,000 plus the $12 for every book. All right, who would like to graph this by hand? Who wants to graph $96,000 by hand on paper?
No one.
No one does. Of course you don't. Absolutely not. So grab your laptop real quick and pull it out. I want to show you Desmos. Yes. Yes. Thank you. Anybody not familiar with Desmos.com? You've all seen, you never heard of it? Okay, well, let's look at it together. Pull up your browser, open a new screen, and we're going to type in the website. It's Desmos.com, D-E-S-M-O-S, www.desmos.com. Can you see that? It's not going to let me zoom that. DESMOS.com. Should look like this when you pull it up. And you'll see the graphing calculator over here. It does not look like your graphing calculator, but it is a graphing calculator. And I really like it because it's super easy to zoom and read. So when you click on graphing calculator, it pops up and it looks like this. We've got our graph area over to the right. And over to the left, we can enter as many equations, and we can do all types of equations. But let's start with this simple linear equation. Y equals 24x. There it is. Now, obviously, we're awfully zoomed in here on numbers like $0, $2, $4, $6. That's not where this equation is going to live, is it? We need to zoom out, so I'm just going to start zooming. I'm going to put my cursor right there and start zooming a little bit. Get it going and get into the 300s, 400s, 500s. You can move it over by grabbing it with your cursor, or grabbing it, excuse me, and dragging it over. If you'll think a minute, most of this whole equation is going to exist in the first quadrant because she's not going to sell a negative number of books, right? And we're not going to make a negative amount of money. Excuse me. So we want to stick over here in this first quadrant. All right, that's our first equation. That's our income equation, and it's red. Mine's red. Let's go create a second equation. If you'll just click underneath the first one. Let's enter our second one, where the dollars equals, that means our y-axis is dollars and our x-axis is books, where y is going to equal 12x. Okay, now here comes the big part, plus 96,000. The blue line just disappeared, didn't it? Take a couple of those zeros away real quick. Just backspace and remove a couple of those zeros. Did the blue line come back? Where's the blue line going when we're adding all those zeros in 96,000? What is 96,000 in that equation? Is that your slope? It's your y-intercept. That means that this equation isn't even starting until way up here at 96,000. Okay, so obviously we need to do a little more zooming out. And then we probably need to shift our graph down so that we can see this area up here where they begin to meet. They're not going to meet until you get above 96,000, are they? They couldn't possibly break even until they've made $96,000 in the books. So let's keep going and find that break-even point. Keep scrolling up. Again, aren't you glad we didn't do this by hand? Okay, did you find the break-even point? Did you find the spot where they meet? Let's zoom in a little bit on that spot. Okay, what can you tell me about the dollars here? How much money are they going to have to make before they break even? What are you seeing over here? Nobody's talking to me. What are we seeing? Zooming in. Where's it breaking even? How many dollars on that y-axis before it breaks even? Somebody say it. $192,000. They've got to make a lot of money before it's going to break even. What is that on our x-axis? How can we know how many books that is? You can click on it for one thing. 8,000 books. If you click on it, you can see that point where they meet right there at $192,000, 8,000 books. So our answer is they need to sell 8,000 books and make $192,000 to break even. Everything after 8,000 books is going to be profit, right? They will have covered their expenses. Make sense? Nod at me. Give me something. All right. So 8,000 books. Write that on your notes. To break even. That point where the two lines cross each other. All right. So right now in your book on page 48, I'm going to have you graph a few of these. I'm going to have you solve and graph a couple of equations. I want you to make sure that you tell me, remember, the answer to a system of equations is a, what am I, you can't see what I'm pointing at. The answer to a system of equations is it's a point, isn't it? That is the answer we're looking for, a point. Or maybe there's no solution. Or maybe there are two parallel lines that lie on top of each other and it's all points or solutions, or it's an infinite number of solutions. But we're looking for a point when we look for our answer. On page 48, I'm going to have you do numbers 33, 35, 37, 39, and 41. Yes, Kaylin. Okay, I'll come look at it with you. I have some Miss Olson graph paper up here, and for many of these, that'll be sufficient for graphing. You're going to need to look at your slope and y-intercept and make sure before you start graphing it that it'll fit. And if it doesn't, you can do it on the back of that graph paper you have. But as many as will fit on here, feel free to use this. Yes, Lane.
I can't see it.
I'm sorry. No, I'll remove that.
Does it end at 39 or is it 41?
41.
41. Okay. There we go, thank you.
The equations look good. So, let's see. So a little bit, you can see that where it's meeting, that point where those two lines are coming together is right here at 192,000. If you touch it, if you push it right over it, touch it. Let's say that point, and you can move it up. That point where it crosses, it's right there. Yeah, I love Desmos for big graphs because it's just easily navigable. Cool website for that. We will definitely be using that again along with our graphing calculators.